Hi all, I am Simranjeet Singh from Samsung Semiconductor India, and I am going to present the work my colleagues at Samsung and I did regarding adoption of portable stimulus standard using virtual prototyping. In the presentation, I will cover a brief introduction of PSS, challenges in PSS adoption, and how virtual prototyping helps overcome these challenges, results, and conclusion. In the current verification approach, tests are created at each level, from IP to system, to meet the verification targets. The tests are created specifically for the verification environment, for example, simulation and emulation. In simulation, we have IP and SoC design verification environments, and in emulation and with silicon, it is mostly system level. At the first level, IP level tests are developed for RTL simulation, mostly using system-wide logic. These tests are quite comprehensive and rely on constrained randomization to meet the coverage. At the SoC level, only few tests are reused. It requires significant effort to create new scenarios, especially IP to IP. For any new scenario, there is dependency on IP verification team to provide the configuration, which has higher turnaround times. In the other verification environments like emulator and silicon, there is no reuse from the SV verification environments. The tests are developed from scratch using C, and it takes significant effort to create scenarios. Across all these environments, many tests have same intent, but the tests need to be recreated. With increasing complexity of the systems and shrinking time to market windows, this approach is not sustainable. So, can we reuse the test across all verification environments with little effort? The solution is Portable Stimulus Standard methodology. In PSS methodology, an abstract model is used to represent the test intent. It contains a set of high-level attributes to specify the configuration of design under test, or the DUT. These attributes can be random in nature, that is, the attributes can be assigned random values. To ensure random values don't lead to invalid configurations, PSS provides support to specify corresponding constraints. The PSS standard specifies a domain-specific language, in short DSL, to develop the PSS models. It also supports C++ implementation. As the model doesn't contain any verification environment-specific information, it can be used across verification environments. Using such PSS models for the system components, high-level scenarios can be defined, which configure the DUT attributes, define control and data paths. To generate tests which can be executed in the given verification environment, it needs a PSS tool. It takes the models and the scenarios as inputs and generates the tests as C or SV code. The C test code is reused with emulator and silicon kind of environments, whereas the SV test code is used for SV based IP and SoC verification environments. The key part of the PSS flows are the APIs. Along with attributes and constraints, the PSS models are also used to specify high-level behavioral code, which binds the generated test to the verification target. These APIs provide the implementation of the high-level functions, which are used in the generated test. The APIs use the PSS model attributes to configure the DUT and verification environment as per the test. Hence, same test can be used for all verification targets. We can create complex scenarios in minutes. However, adoption of PSS is not easy and comes with its own challenges. The PSS models and APIs need effort to be created to generate tests. As PSS supports randomization of attributes, the constraints need to be specified correctly to rule out all invalid combinations of attribute values, or simply generate no invalid configurations unknowingly. If there is bug in the constraint specification, the generated configuration could be invalid. Similarly, if there is coding bug in the APIs, the DUT will not be correctly configured, which will result in test failure. Now, the user wouldn't know where the issue is and might spend significant time and effort to debug failures due to PSS model bugs. So we need to validate the PSS model with the DUT itself before it can be used. To validate the PSS model, we could look at RTL simulation as it is available early, but the simulation speed is too low and debugging issues is complex and time consuming. With each iteration adding to overall time to validate the model, this approach is really not feasible. We could use emulator for validation. It has faster execution speed and supports software debug tools which help debugging issues, but there is no support for RTL source code debugging. It requires waveforms to be dumped and analyzed, which is time-consuming activity. In addition, it's an expensive resource and is not easily available. It takes hours to get the license and execute a test. And most importantly, it is available at a later stage, which again means PSS will be too late for deployment. So using RTL simulation and emulation is not feasible. We need an approach to validate the models fast and early. And the solution is virtual prototyping. A virtual prototype is a functionally accurate transaction level model of hardware. It's an abstract model developed using C++ System C, which makes it easy to develop and is available early. It has faster simulation speed in the range of 100 times faster than the RTL simulation. So virtual prototyping is a good candidate to validate the PSS model. A virtual prototype contains the abstract model for all key components. For CPU, it uses instruction set simulation models which can execute the binaries compiled for the target CPU in the hardware. These models support software debug tools like Trace32, which makes it easy to debug C code being executed using features like stepping through the code, putting breakpoints, analyzing memory content, and DOT configuration. It has a bus model with accurate memory map. For other IPs like multimedia, at the core of these VP models are the corresponding functional models. These functional models are pure C or C++ models and are considered as golden models as they are also used as reference in IP verification environments to validate RTL output. As these models are in C, these can be easily integrated in a VP. It ensures that the VP results match the RTL results. On top of these pure functional models, VP models provide the register support along with the interrupts. Hence, VP models mimic the IP functionality and all the key interfaces to execute tests as if running on actual hardware. This makes VP an ideal candidate for PSS model validation. The user APIs are a critical part of the PSS methodology and require significant effort. These APIs are what binds the PSS generated test to the verification target, and hence these are verification target specific APIs. The system Verilog is used to create the APIs for system Verilog based simulation environments, whereas C is used for CPU based verification environments like emulation, silicon, and VP. Having different implementation of these APIs for C and SV environments may lead to inconsistent behavior across verification environments, which makes it difficult to reproduce issues and debug. To avoid the effort of creating target-specific APIs and to avoid inconsistencies, a uniform implementation API is needed, which we can achieve by using C. With C APIs, PSS-generated tests can be used at system-level testing environments like emulators, silicon, and BP. The C APIs and the generated C test can be cross-compiled for the target CPU, and the binaries can be used across verification environments. For system Verilog-based simulation verification, the C APIs can be reused using the C-SV Direct Programming Interface or the DPI. And all the register and memory accesses from C APIs are mapped to the equivalent SV task. Additionally, it can be used in VP unit level testing environment that is without CPU models. The generated test and C APIs are compiled natively and executed as part of the test bench. Here is a simplified example of a PSS model. A component named DUT_C is being declared. It has an action called do_operation, which is used to create the scenario. In the action, DUT configuration object is being instantiated, which has all the attributes and relative constraint information. In the execution body, procedural code is being specified, which is generated by the PSS tools as part of the test code. In the exec body, the high-level C API functions are called to configure DUT, which takes the DUT configuration object as input, configures and triggers the DUT, and another function check_DUT which performs relevant checks. In the C APIs, the function configure DUT performs the DUT configuration with the PSS attribute values using the write register function. The write register implementation is controlled using compiler directives to perform write operations specific to the verification environment. For system Verilog environments, it calls corresponding SV task which performs the write using a VIP like APB or AHB. For VP unit test environment, it calls a function which performs the write by calling a VP test bench function. And for CPU based environment, it performs direct data write at the register address, which translates to load instruction in the cross compiled library. Same approach is used to handle the read operations. This slide shows an example of a scenario created using the DUT action do operation. In the scenario, the attributes input format and the output format of the DUT configuration object are being fixed. The rest of the attributes will be assigned randomly generated values. Here is a simplified version of the test code generated by the tool for the example scenario. In the generated code, the DUT conf object is being created. Its attributes are initialized with the values fixed from the scenario for input format and the output format, and for other attributes, the values are picked randomly as per the constraints. Eventually, it calls the C API function along with the needed arguments as specified in the exec block. With VP, the generated C test is compiled with target CPU toolchain. The resulted binary is loaded in the VP and run. Due to its high simulation speed, thousands of test cases can be executed in short time. To support automated checking with PSS, checks are added to the implementation APIs. One category of checks are related to interrupt integrity checks to ensure that all relevant interrupts are triggered, like frame start and frame done for multimedia IPs. If there are no interrupts or error interrupts, the test is declared as failed. As VP supports most interrupts including error interrupts, we can verify these checks with VP-based verification. For data integrity, the DUT output is compared to the reference or golden data which is obtained using functional models. As VP have these C models or these function models at its core, it ensures the VP output matches the DUT output. To be able to perform data integrity checks, PSS needs a flow to capture the golden data for the generated test. Generally, the functional or C model takes a configuration file as input, which specifies the C model parameters and their values. The PSS specification allows users to generate any kind of file using PSS tool. Using this feature, the C model config file is generated from the PSS model, and the parameter values are derived from the generated configuration. Using the PSS tool, the config file is generated along with the C test kit and run with the C model. The golden data can be either plain binary or its CRC value. If it is CRC, it is captured in the C file and is compiled with the APIs which compares this golden CRC against the CRC from the DUT. If there is no CRC, the golden data is loaded in the memory at a pre-decided address and the APIs compare it with the DUT output. The code snippet here shows how the checks are added in the C APIs. As part of the DUT configuration function, user function is called which updates the golden data for the test. For example, storing CRC value from the C model output. And function to register interrupt handlers. In the interrupt handlers, a flag is being set to notify that the particular interrupt is received. After the configuration and triggering of the DUT, the check DUT function is called. In this function, it waits for the flag which is set from the interrupt handler as shown in the previous slide. When the interrupt is raised, the interrupt handler is invoked, which sets the flag. When the flag is set indicating that the end interrupt has been received, it checks all the relevant interrupts are received and there are no error interrupts. Finally, it compares the golden CRC with the CRC from the DUT registers. In the cases where CRC mechanism is not available, the DUT output, which is written to the memory, is compared with the preloaded golden data. Using this approach, the test status can be determined whether it's passed or failed. Another advantage that VP offers is ease of debugging. As discussed earlier, VP models are C++ models which can be debugged with tools like GDB. Users can set breakpoints or watch points in the model code for debugging issues. Due to its fast simulation speed, multiple iterations to fix an issue can be done in short time. Many EDA tools offer support for capturing and viewing register traces. It captures all the register accesses over a period of time, which helps identify issues in the APIs. It also makes it easy to debug error conditions which could occur due to issues like missing register writes. As mentioned earlier, the CPU instruction set simulation model supports tools like Trace32, which allow users to debug the test being executed on the CPU. Users can set breakpoints and watch points in the test code and can analyze memory contents. Additionally, users can change CPU register values or update test variable values to trigger specific behavior. All these features greatly reduce the debug effort. At Samsung, we developed the PSS model and the C APIs to verify a display subsystem, which was quite complex subsystem. We identified around 70 attributes and specified the relevant constraints. Using randomization, we generated little more than 2000 test cases to ensure validity of the PSS model. To run these scenarios, we use a simple virtual prototype with the Cortex M0 model and the display subsystem. We could execute all the 2000 test cases with VP in under 5 hours. By running all the tests, we identified many issues with the PSS model constraints along with the bugs in the APIs. With the many debug features of the virtual prototype and faster execution, we could easily identify the root cause. Another advantage with VP was that we set up the regression which would execute large number of tests nightly. It helped us keep the ongoing PSS model and API development in check. Once the PSS model and the APIs were stable on the VP, we eventually used the PSS model to generate tests for simulation and emulation environments. We executed the generated tests in both simulation and emulation environment using the same C APIs. As the PSS model was stable, we could successfully run around 80 tests in simulation and more than 100 test cases in emulation. We still found some issues in the PSS model constraints as these constraints were not documented and some scenarios were not handled properly in the VP and its functional model. As we use the same C APIs for all the environments, we could easily reproduce the failure in the VP and emulator environments for further analysis. It helped us save a lot of time and effort as a failure in simulation environment could really take up days to debug and fix. Considering the effort to validate the PSS model in the three environments, VP, simulation and emulation, the PSS test creation effort is same for all as the same model and C APIs are used. However, the test execution takes less than 5 minutes in VP, whereas in simulation it can take more than 7 hours. With emulation, the execution time is less than 10 minutes, but the license wait time is around 2 hours on average. And on busy days, it can go up to 10 hours as well. On the debug support side, the source code debug is available in VP and simulation, though the VP it's only the VP model code, whereas with simulation, the RTL source code can be debugged. There is no source code debug support available in the emulation environment. As discussed earlier, it requires the waveforms to be captured and analyzed. On the waveform support, all three environments support waveform capturing. The register view support is available only in the VP and emulation environments. Similarly, the memory view support is only in the VP and emulation. As we can see, with VP's faster simulation speed and ease of debugging significantly reduce the effort of qualifying the PSS models. In conclusion, PSS model validation is the biggest challenge in adopting PSS methodology. Validation with RTL simulation or emulation is not feasible to meet the verification schedule. VP with its early availability, faster simulation speed, and ease of debugging is the ideal candidate to validate PSS models. VP helps identify majority of PSS model bugs upfront, saving significant effort of debugging with RTL simulation or emulation. For more information on PSS and System C, please refer to the sources provided by Accellera and other links mentioned here. Thank you.